Now, what I'm going to do is look at the long-term solutions of arithmetic and geometric sequences. Just before I start, let's recall what I've taught you. What's the difference between geometric sequences and arithmetic sequences? Aisha, 1 point. Give me 1 point. All right, I'll come back to you. Yes, Justin?
Geometric sequences have ratios, whereas arithmetic go up by a certain number each time.
Thank you. So, geometric sequence has a common ratio. Arithmetic sequence actually has a common difference. All right? So that's one thing. So difference is there. Which one is linear, Isabella? Arithmetic is linear. So with geometric sequence, close your laptop, please. You don't need your laptop now. With the geometric sequence, generally, how do I describe the graph? Riley? Exponential, that's good. So, is geometric sequences always exponential, Monty?
Yes.
Yeah, negative ratio.
Thank you. So there is not always exponential. If you have negative common ratio, go up and down. Very good. So most of you remember what I taught you. So let's have a look at today. Today is going to be something that you need to be able to plot graph and recognize the graph. All right. So what we're going to do is determine the long-term solution of an arithmetic sequence. Describe and determine the long-term solution, including steady-state solution for geometric sequence, and able to plot the sequences on a Cartesian plane. All right. So the word steady-state, keep that in mind, because the next sequence we are looking at, that is really important, steady-state solution. We're going to start off. Let's talk about sequences. Sequences may be displayed in a tabular form. The top row displays the term number of the sequence, which is independent variable. If you think about it as x and y, that's x, and then the bottom row display the term values of the sequence, which is a dependent variable. All right? Now, sequences in the table format. You can see that the first row, that is the term number, which is n, 1, 2, 3, 4, 5, 6, 7. And since you know T1 is 2, that is T1. So that bit here, that's T1, that is n. All right, which is equal to 1. So you can see that with that, think about your x and y, that's x, that's your y. That's your equation to bring it up. And plus 3, that is your common difference. All right? When graphing a sequence, the term number is the independent variable and is represented by the horizontal axis. So remember, n is the horizontal axis, whereas the value of the term is the dependent. The value is the dependent variable and it's a vertical axis, which is y. All right, so x and y. Now, this is how I would graph a arithmetic sequence. If you look at this situation here, you know T1 equals to 2. Start off with 1, I've got 2. And then plus 3, that is 2 plus 3, which is 5. This is 4, 6, 8, 12, all right? So that's 5, and then 8, and then so on and so forth. The common difference is positive, therefore this is increasing, all right? So you can see that the slope is actually a positive slope going up. And positive slope, think about the word increasing. Whereas in this situation, you are taking away 5. And you can see that there's a negative slope, and negative is decreasing. All right? Yeah? So in this case, as n is increasing, t is decreasing, tn is decreasing. As n is increasing, tn is increasing. Now, how are we going to describe this? So when d is greater than 0, we have actually long-term increasing solution. Whereas when d is less than 0, it's a long-term decreasing solution. So think about the slope. One is long-term increasing, the other one is long-term decreasing. Positive, increase, negative, decrease. All right? Use that, link that for your arithmetic sequence. Pretty straightforward arithmetic sequence. You know the slope is up or down only. Now, when we come to graphical display of geometric sequence, a little bit more complicated. So let's think about when a is equals to greater than 0. All right? So, positive first term, a equals to 0, you've got two situations. You may have r, which is greater than 1, the ratio greater than 1, or r is between 0 and 1. It cannot be 0, it cannot be 1. If it is 1, it's just a straight line. All right? Yeah? So if you think about this situation, with a greater than 0 and r is greater than 0, what happened? It's actually increasing, correct? So, for example, you're multiplying this by 2. Example, e.g., you're multiplying this term by 2. By 2. By 2. So you can see that r is greater than 1. It will increase. Whereas in this sort of situation, you could think about it as multiplied by maybe 1/3. So it keep on decreasing. So these two situations there. A greater than 0, r greater than 0, you've got the long-term increasing solution, which is growth. Whereas when you've got r greater than 0, a greater than 0, r is between 0 and 1, you've got long-term steady state solution, decay. The reason why I say steady state is because it's approaching 0. All right? It's approaching 0, and it will go on and on and on, and it will sort of have a number which will not change much. It's getting closer and closer and closer to 0. So you've got a long-term steady state solution, you've got a long-term increasing solution. All right? Any question before I move on? Now, what if a is less than 0? Oh, sorry, a is still greater than 0, and then you've got negative number. R, the first situation is when r is between -1 and 0, and the other one is r is less than 1. All right, so here in this case, let's say, because a is greater, let's think about this as multiplied by -half. All right, from a positive number, it will become a negative. And then if I multiply it by -half again, it's going up to positive, and then down, up and down, up and down, right? Whereas the next situation, if I've got this as greater than 1, let's say multiply it by 2, -2, positive to negative, negative to positive, correct? Times -2. All right. So let me draw something. What happened? It will look something like this, right? Whereas in this situation, it will be opening up. Yeah. So how do we describe it? The first one, we have a long-term steady state solution. Again, in this situation, it's actually approaching 0. There is no long-term solution at all. It's going up and up and up and up and up. All right? It's up either there or there, there or there. So there's actually no long-term solution. So you need to be able to describe it, whether there's long-term steady state or whether there's no long-term steady state. So geometric sequences is a little bit trickier. You must be able to recognize these 4 situations. There are 4 more coming up. Basically, I've just shown you when a is greater than 0. What if it is negative? A is less than 0. Do you get the same sort of solution? Let's have a look. Alright? So this time, when a is less than 0, but r is greater than 1. So in this case, you've got, let's say this is multiplied by 2. Multiplied by 2. Alright? So it is, let's say this is minus 1. Then we'll go to minus 2, minus 4, and so on and so forth. So it is growing, and what happened is that is going to be really long term, going larger and larger. Whereas this one, let's say this is multiplied by maybe multiplied by half. It's going slower and it's actually approaching 0. So here you have a graph something like this, approaching 0. Whereas this one, it will go on and on and on that way. That is closer to 0. So here, again, you've got long-term decreasing solution for the first situation. Second situation, the long-term steady state solution. So when it approaches a number, getting closer and closer to a number, that's always long-term steady state solution. All right? This sort of situation is the same. What do I have? I've got that. What is it approaching? 0. Yeah? So there is a long-term steady state solution. Whereas in this situation, it could be up or down, up or down. There's actually no long-term solution at all. All right? So what I want you to get to understand is what is a long-term steady state solution, why it's no long-term solution. And you've got long-term decreasing and long-term increasing. All right? This is a summary. You can print it out and stick it in your book. It's basically what I've explained to you but summarized. It's also in your book. This is directly taken out from the book. So I'm not going to worry about going through everything at all. All right, just for you to read. Now, let's go to example 1 in your book, which is exercise 5I, please. Exercise 5I, I'm going to show you 4 examples. 1, 2, 3, and 4. Let's look at this one here. Now, consider the recurrence relation. You got t n plus 1 equals to t n minus 2. T n equals to 1. Sorry, not 1. T n is equal to 15. So can you actually complete the table? What you need to do is start off with n. You know the first number, first n is 1. So that's 1, 2, 3, 4, 5, 6, and then there's 15 there. Can you fill that table in, please? If you haven't got a book yet, if you need a graph paper, I have some graph papers. Anyone need graph papers? Can you, if not, just take a picture, please? Take a photo of it. All right, you should be able to write out a sequence. Starting from n, starting from 15, a should go from 15. Take away 2 is 13, 11, 9, 7, and 5, correct? Now, plotting the graph. If you've got the book, it's pretty straightforward because you know the first point will be here, 15, and then 13. Now, please make sure that you plot it carefully. Either use a dot or use a cross. All right? It could be a cross like this. It could be a dot. All right? Make sure that it's right there. 1 and 15. All right. Now, is this linear? So is this a is this arithmetic or geometric sequence? Arithmetic. And so, does it have a long-term increasing or decreasing solution?
Increasing.
Yeah? Sorry? Oh, yeah, sorry. My fault. Sorry about that. Sorry, did I? I was too involved with that. Alright, so when you draw something like this, make sure that, like I say, make it really clear and use darker pencil. So we have got long-term decreasing solution in this case. Alright, go ahead and do question 2, please.
Long-term decrease now it's arithmetic, and if it was geometric, it would be on long-term steady state decrease.
I mean, all you need to do is graph the thing.
No, I'm just saying.
You need to be able to graph the thing because you are
Yeah.
expected to graph the thing.
Arithmetic, like this would be long-term steady state.
Alright, example 2 is question 2. So this time you need to draw the table as well.
This would be long-term steady state. This would be
I think this is long-term decrease. Wait, let
steady
me see.
state. Steady state because it never reaches zero.
Yeah, but it's decay still.
Yeah, but it's
decay,
still-
yeah, steady state. Because it approaches zero. Anything that approaches zero is steady state.
But
But that's nothing,
is
right?
just
No
long-term.
long-term. No long-term.
No long-term.
No long. On. No, because that approaches zero.
So is this a
No
geometric
long-term
or arithmetic
solution,
sequence?
steady
state.
state, long-term steady
That's
state.
correct.
Yeah, okay, it's steady.
Yeah, long-term
Growth,
increasing.
decay. What would these ones be?
That's long-term decreasing.
So is this an arithmetic or geometric sequence?
Steady
Steady
state.
state.
No motion. Yeah.
And this, and when it comes to arithmetic, it's just
Arithmetic just use if it's growing, then it's increasing.
long-term decrease. Yeah, but it can't be steady state.
So this is the table,
Oh, because it would always.
and I will fill in.
Go through.
Now, in this situation, I will only go up to 5 because see here, you've got 1, 2, 3, 4, 5. You've got 5 numbers only, so I have the table up to 5. I just follow the axis. So n is from 1 to 5. That's it. You need. This is like listing the first 5 sequence. So with this, sometimes in the exam or test, they'll give you a table, and you should be able to interpret the table. All right. Top row is always n, bottom row is tn, and of course read what they say here. All right. That's important. You've got that. Now, arithmetic or geometric?
Geometric.
Geometric, thank you. So if it is geometric and you know that the ratio is, common ratio is 2, positive number, and starting point is negative number. So what would happen? Is it going to curve downwards or curve upwards?
Downwards.
Downwards, thank you. So that's what it looks like. Now, what type of sequences is being defined by this recurrence relation? Here, I've asked you, justify. Answering this sort of question, you need to justify it by working out the ratio, or just showing that each, just explain that the subsequent number is the previous number multiplied by 2. All right. So this is geometric. So each subsequent number is the previous number multiplied by by a common ratio of 2. Alright? So does the recurrence relation have long-term increasing, decreasing, or steady state? Decreasing because it's approaching negative. So it's long-term decreasing. Alright? Let's go to example 3, which is question 3, please. Of course, same thing. You fill in your 1, 2, 3, 4, 5, 6. Look at what is given in axis. It's given you 6 numbers, 1 to 6, n1 to n equals 1 to 6. So in the table, do the same thing as well.
Steady state, no? I have no idea.
All right. Approaches number. So it goes like in this situation, very, very, very close to 0.
Because you can never halve the number to get to 0.
Yeah, it's approaches.
But it's approaching
Yeah.
still.
No, but I think you can steady state if it approaches any.
All right. As long as
Just,
it approaches
you know,
number.
but how it gets on there.
I don't know how we're approaching number that's not 0. Because when you just
All right.
halve it,
So this is
Yeah.
what I've got.
maybe it's like
Now-
fractions really weird.
Is this a geometric sequence or a arithmetic? Geometric. You need to be able to justify. See example 2. All right. Geometric. There's a common ratio of minus 0.5. All right. So look at this. If you draw a line, is it approaching 0?
Yeah.
So it has a steady state solution, long-term steady state solution. In the long run, its approach is 0, although it's hovering up and down 0, but it approaches 0. Therefore, there's a long-term steady state solution. Yes? Sorry? What did, sorry?
It's example 4.
Example 4, did I?
Yeah.
That's mine. Just go to example 4, my fault. Just do example 4.
I was on negative 2 times.
All right. Which means I use a different example. I use question 4 in the book, not question 3. So this should be question 5. All right. This should be question 5. I skip because question 5. So that's question 3. That's question 5. Can you do this, please?
Did we just do
Sorry?
Oh, no, that's fine. That's fine.
All right. Okay. So I skipped question 3 in the book. I did question 4 and 5. Don't know why. Do question 5, but you get the gist of it. You get the gist of how to answer this question.
Basically, the guy wrote the hardest test.
Mr. Chloe just cheeky.
this is my solution. And what does it look like? So if you look at the shape, there's actually no solution at all. There's no long-term solution. Could be negative, could be positive. It's not, you don't know whether it's increasing or decreasing. All right? And you know that it's a geometric sequence. All right, I'm actually going to stop here and just doing a quick summary of this lesson. All right? Think about when you plot. When you plot the graph. All right? This is n. This is Tn. Now, it could be a straight line. That would be arithmetic. And that is long-term decreasing. All right? Because it's pointing downwards. Long-term decreasing. What you need to look at is look at whether it's a straight line. If it is pointing down this way, it is long-term decreasing. Whereas you may have situation that goes this way. I use different symbol. All right? That is actually long-term increasing. It's a linear and long-term increasing. Yeah? So next situation, let's talk about geometric sequence. If I start off with something which is above, all right, that's T1. And my R is a positive value and greater than 1, it will always go up that way. Correct? Yeah? So let's say it's times 2, and that is long-term increasing. And it's an exponential function. It keeps going up, and it's always towards positive. What if I have this situation? I start off with a number here, and this time R is between 0 and 1. I'll go down. All right. This time I am approaching. Oops. Let me use the red. I'm really approaching 0. I will go closer and closer to 0, but it will never be 0. So that's a long-term steady solution. Long-term steady state is approaching 0. Same with if I've got R. A actually starting with negative number. All right, I might go all the way with R greater than 1. So R is greater than 1. You can see that it is going that way. And that's a long-term decreasing solution because it's going to negative. Whereas if I start from here, I might go down this way, and it's approaching 0. Again, when it is approaching 0, that's a long-term steady state solution. All right? Then we've got situation where you will have, I'm just going to draw the general shape. Either this, when you've got a negative ratio. All right, I've got a negative ratio. It doesn't matter whether I start positive or negative. It will go alternate between positive and negative. Correct? In this sort of situation, there's a long-term steady state solution. All right? Whereas I may have something like this. Which means there's no long-term steady state solution, there's no long-term solution, because you don't know whether it's ending up in negative or positive. All right? So I'm going to stop here today, and you should have plenty of exercises to do.